About our last chapter, the capacitors, and I picked some questions from our textbook and also from survey. So the first question is about, so I'm going to also send this document as a PDF and add them up in this Teams, and then also in the other online material. So here is the question. This is a circuit, and 4 microfarad, 7, 5, and 6, and it is connected like this. So what is the equivalent capacity in this one? And what we are going to do here is, and also the next question is, what is the charge distribution of these capacitors? All right. So we know a straight line always have the same potential. So we know that from our potential chapter, any surface of the material should have the same potential. So what that means is, if you put, for example, some letters to this, so if I put A here, this will be the point A, and if that's point B, that will be the point B, and this will be, for example, point C, because you will have a capacitor here. So what we need to do, also, you can also take this point and then carry it over. So so this is also point A here, and that is point B. And then if you just rotate the whole thing, right? So it looks like this. So basically, what we have is this thing. All right. So so it's quite obvious whether they are series or parallel in connection. Okay. So next, what we can do here is that. So these two guys are in series. So what we need to do is 1/5, 1/7, and you take an inverse, and that is 35/12 microfarad, these two guys. And these three will be in parallel. So what we are doing in parallel is you're just adding up the capacitance. So 4 plus 6 plus 35/12, and that is 155/12. Microfarad. And next, so what would be the charge distribution? And so it will be Q1 going in here, Q2 and Q4. Since these are in series, whatever the charge here will have the same charge here. So if I call this Q2 and that is Q3, those two will be equal to each other. So Q3 and Q2 will be equal to each other. So so the total charge Q is coming from here, this total charge Q, and it's divided into 3. All right. So what we know is, since this is point A, that is point B, the potential here are all the same, and the charge is distributed or shared according to that potential and the capacity. So VAB potential for this guy is Q1 over 4 microfarad. Q2 will be Q2 divided by 35/12, and Q4 would be like once we divide it by 6, that will be VAB. So these are the relation between the charges. So next, if we call Q1 to be Q, then we can write everything in terms of Q. So Q4 would be 3/2 times Q. And next, all right. So next, what we have is Q2 and Q3, and that would be also this thing. If I call this Q, that will be 35/48 times Q. So those are the relation between the charges. All right. So this is this was rather a simple question. And so our next question would be this one. All right. So so the question starts like this. 50 volts is charging those two capacitors, which has, one of them has 25 microfarad and the other is 40 microfarad. And then the battery is disconnected, and the capacitors are separated. So we disconnect the battery and then we cut these lines out. Okay. And the next is, if the capacity or the capacitors are connected from their opposite charges facing each other. So connected oppositely, what are their final charges and what are their potential, final potential? All right. So, and that's the question. And let's move to the answer to that question. So first, we need to find out what the charge, the initial charge of the system. So initially, it has, they are all parallel like this, right? And the potential is 50 volts. So they have charges according to the potential, and Q is equal to C times E. So we can find Q1 to be 50 times 24. That is 1250 microcoulomb. And that is 50 times 40 is 2000 microcoulomb. And again, here, don't forget about micros. Okay, so if you have a micro that that is 10 to the minus 6, and that will carry over to your next answer. So farad times volt is equal to coulomb. Okay, so that is capacity times voltage is equal to the charge. All right, so don't forget about the micros. And next, so the question starts actually here. And if we connected them with like the positive charges here and negative charges there, so like oppositely connected, all right? So what's going to happen is that they're going to have the new charge distributions. So if I say this 25 microfarad has Q1, and once they are equilibrated, like they come to some like static thing, and then this Q1 prime will have a new value and Q2 prime will have a new value. And obviously the potential would have a new value. So if I call this like VAB here, so the old VAB is, let's say, 50 volts, and VAB prime would be also being asked. Okay. All right. So next, the total charge will be, shared between the capacitors, and so what's going to happen to the total charge? Since they are, connected oppositely, they're going to cancel some of the, some of the total charge. So 1250 minus 2000, and it is minus 750 on the side. Okay, so it will be like minus 750 here, and on that side, or like what I should say, maybe I should write it like this. So once you equilibrate this thing, this will have a minus charge here, because the amount of minus here are more, and that would have like positive charge here. Okay. And the Q1 prime and Q2 prime are not going to be equal to each other. So we can always work with the absolute value of the 750, say minus 750. All right. So because the total charge would have the 750 microcoulomb, and next, this delta V prime is equal to Q1 prime by C is equal to Q2 prime by C2. And since we've plugged in the values here of the capacities, then Q1 would have 25 by 40 of Q2, or 5 over 8. And we know the total charge is 750, and we can solve for Q2 here, and Q2 would be something about, yes, so Q2 would be this number, which is 461.5 microcoulomb, and Q1 would be 288.5 microcoulomb, which, the total would be 750. And next, you can also find out what is our new voltage, new potential difference. And you can just like either use this one or that one, it doesn't really matter. You can plug in the values and then say, what would be the new potential, and 288.5 divided by 25, that is 11.5 volts. So that's our new potential. Okay, and so we can also add some extra question. What happened to the energy? So ratio of the energy stored before and after, so we can find out how much of the energy is being lost after they cancel out some of the equations, some of the charges. So the total potential energy is U1 plus U2, let's say. So this is initial, when this was charged with 50 volts. Okay, so you can say, so this is the energy formula, remember, 1/2 C times V square, and we have two capacitors, and then we can add them up. So initially it is 93,750 microjoules. Again, pay attention that we have a micro here, okay? And so U2 prime, finally UT prime, the total prime, would be our new potential. Okay, so C1 and C2 are the same, but our new potential is 11.5. So if we plug in the value in the equation, we'll get a 4,959.4 microjoules. And so we can take a ratio of these two guys. So we can say, what is the lost energy? So the lost energy is basically, I mean, you can take, let's say, the absolute value of delta U. You know, this is the initial, that's the final one. And the lost energy is somewhere around like 89,000. And so if you want to find the percentage of the lost energy, that is the lost energy, this guy. And UT is the 93,750, and we'll see that 95% of the energy is being lost. And that's due to most of the charges are, you know, they cancel each other, right? The positive and the negative charge. So, so most of the energy is gone there. All right. Okay, any questions? Sorunuz var mı arkadaşlar?
Hocam.
Evet.
Orada 25 ile 40'ı toplamayacak mıydık? 50'yi topladık da işlemlerde. Ben mi yanlış yaptım?
Evet. Burada
değil
şey
mi?
var aslında. Evet. Haklısınız. Ben orada bir işlem hatası yapmışım.
Tamam.
Yani burası aslında hani 40 olacak. Şurası. Şunlar. Evet, onu düzeltmem gerekiyor. Yani 40 artı 65. Hani şunu bir düzelteyim. Bunu bir düzelteyim. Ama hani ratio'lara bakacak olursak aslında hani şurada 40, şurası doğru herhalde değil mi? Burada bir hata yapmadık. Evet, evet 25 ve 40 olacak. Teşekkür ederim. Ama hani şuradan da şeyleri yaparsak eğer hani işlemleri hani delta U dediğimiz zaman hani C'ler zaten hani götürüyor aslında. Yani delta U is 1/2 C1 plus C2. That is, let's say, delta V prime square. Yani bu da işte delta V square divided by işte 1/2 C1 C2 delta V square. Yani buradaki hani sonuç aslında 11.5 square minus 50 square divided by 50 square oluyor. Yani bunun da absolute value'sunu alıyoruz ki pozitif bir değer çıksın. Onu da hemencik yaparsak şu çıkıyor arkadaşlar. Yine aynı şey mi çıkacak acaba? Hemen hesap makinesiyle bir bakayım. Bölü 50 square. Yine evet 0.94.7 çıkıyor. Yine aslında hani %95 değişmiyor arkadaşlar burada. Çünkü oranla birbirini götürdüğü için, ama şu oranlar şey, bunları düzeltmem gerekiyor. Onları ben bir düzelteyim. Düzelttikten sonra da bu dokümanı ben doğru şekilde koymuş olurum. Peki, teşekkür ederim. Bir sonraki soruya geçelim. Alright, so this is from our book, from textbook. I don't remember the number of it. So what we have here is C1, C1 on the sides, and C2, C2 here, and C1 here. And C1 is given to be 6.9 microfarad, and C2 is 4.6 microfarad, and VAB is given as 420 volts. And the next question is, what is the C equivalent between A and B? And what is the charge distribution on each? And what would be VCD, the point, the potential between these 2 points? All right. So next, let's figure out what would be our capacity. So here we see that these three are parallel. Sorry, in series, right? So these three, I can just like take this guy and put it here, and take this guy, put it here. These three will be in series. So what we have is C1 over 3, and that is 6.9 divided by 3, 2.3 microfarad. And these two will be in parallel. So that means we're going to add them up. So 4.6 plus 2.3, and that is 6.9. So these two things are basically equal to the magnitude of C1. And that's actually the trick of the question. So it seems a little bit, so if you want to do it with just like using letters without the values, you will have a bunch of equation at the end, and then that will be much more complicated. But these two, since this is like 2/3 of the first one, so it makes up to be a new, in a special case, let's say. All right. So next, so these two has a C1 or like 6.9 microfarad equivalent capacity, and then we get the same picture here again. C1, C1, and C1, right? Or we're going to have 2.3 microfarad again here. All right. So next we're going to move on, and we will have the same picture. Again, these three will make up to be 2.3 because they are in series, right? 6.3 divided by 3. And then these two will be in parallel. And again, that will, these two, if we add them up, we're going to get 6.9. And finally, at the end, so what we have, C1, 6.9 C1, and that is equal to B, again, 2.3, 6.9 divided by 3, 2.3 microfarad is the equivalent capacity between point A and B. So, okay. So the first part is done. The next part was what would be the charge distribution? All right. So we know that what would be the total charge, and we're going to find the total charge, and then we're going to distribute it by just going back, right? And let's figure out the total charge is equal to C times delta V. That is our total. That is the potential between A and B points. So this is A, that is B. And Q would be 966 microcoulomb. Okay, this guy times 420. All right, 2.3 times 420. So that is roughly 1,000 or 966. So next, so we're gonna go back. So the way that we do it is I'm gonna put more and more, and then put the charges on each capacitors. So in this part, so how did we figure this out? We said these three are in series, and that's how we got that. So in series, it's always the capacitors will have the same charges always, right? So then the total charge 966 will be the same, 966, 966, and 966 here. Okay, so I can also figure out what would be the potential of this guy, right? So in series, okay, so let's maybe like right here. So in series connections, charge are the same, and potential is like shared, let's say, or distributed. Okay, so at each point you can find the potential. So since these three are equal, that means the potential here, this delta V, if I put like X and Y points here, this delta V would be 420, or three of these potentials, delta V here, delta V here, and delta V, this 3 delta V would be equal to 420, and that makes it 140 volts. So this is the potential between VXY points. All right, so next what we need to do, we have to add them up. So remember how we got this. So the 6.9 was the combination of these two parallel capacitors, right? Which one of them is like 4.6, the other is 2.3. So we know since these are parallel, that means this point X will be the same point here, X, and Y will be the points here, the same potential. That means that the potentials are the same. So here, so in series, we said Q are the same and V is shared in, so in parallel, the potential is the same and Q is shared. Okay, so in here, these two are parallel, so that means the charges will be shared. So how are we going to distribute the charges? So since the potentials are the same, which is 140, that is equal to, if I call the charge of this guy is Q1, and that is Q2. So Q1 divided by 4.6, Q2 divided by 2.3, and the total of the charges would be 966. So if you solve this question, then Q1 is 644, and Q2 will be 322 microcoulomb. Right. Okay. So we have one more step to go, and I'm gonna go to the next. Oh no, here maybe. And the next is, remember how we figured this out. So these this was the equivalent of the three capacity which are in series, right? So 2.3 comes from 6.9, 6.9, 6.9 being in series, okay? And the question also asks, so these are XY points, and these, so one of the question asks is, what is the potential between points C and D? Okay, maybe well, let me just like write out what VCD is. Okay, so VCD, since so this has charge Q2, this guy 2.3. So 2.3, this will have the same charge to which is 322 microcoulomb. This has the same Q2 charge. This has the same Q2 charge. So if you want to figure out what is the potential here, VCD, so that potential is the charge divided by the capacity value. So that would be 322 divided by 6.9, and that is 46.7. Okay, and so let me just rewrite it. So again, so we are here, this was XY point, that's CD point, okay? And then next, you know, remember what I'm rewriting whatever I told you in the previous page. So here, again, these are XY points here, that's XY, and then that was the 6.9, 6.9, 6.9, okay? So if we also extend this thing in a previous setup, so you know 6.9, 6.9, 6.9 makes it 2.3, right? So that's what we find out. All right, so and as a last point, what would be, so if we also extend this part, sorry, this part also 2.3, so that will have the same 6.9, 6.9, 6.9, okay? So that's like 2.3, that's the last branch that we have right now. And so this 2.3 is again these two things. So whatever the charges here, so we found this Q3 to be, what did we find it out? All right, so let me just check the previous page. Okay, this was, so Q2 was 222. Okay, so this is 222 here. So this, sorry, 322 charge, 322 coulomb, microcoulomb, is being distributed according to this connection. So this means these are parallel. So this Q2 is equal to Q3 plus Q4. And here, since this is VCD point, that is point C, that is point D, okay? So VCD is equal to Q3 divided by 4.6, right? This guy, or Q4 divided by 2.3. And you can also find out what would be these Q3 and Q4, and one of them is 214.7, and the other is 107.3 microcoulomb. Okay. All right, so you can also find out, since this was the last branch, and you can take that to be also 6.9, 6.9, 6.9, and then you can find out what would be, if I call this like WZ, what would be the potential of WZ. That is 1/3 of the VCD potential. So that would be 140 divided by 9, okay? And which makes up to be like 15.5. Okay, so as a summary, so that's the, all right. So that's the summary of the question. Right. So we started and we found out the C equivalent, and C equivalent we found out to be 2.3 microfarad. And then the next, what we did was find out the total charges. So in this picture, so I put in every value of the capacity value and the charge value, and then I also put the potential between 2 points. Okay, so for example, this is 420 volts. So the potential between these 2 points is 140. Potential between these 2 points is 140 divided by 3, which is VCD. And potential between these 2 points will be 140 divided by 9. So it is, what you see is like 1/3 of it always. Okay, so it is 140 divided by 3, 140 divided by 3, 420 divided by 3, that is 140. 140 divided by 3, and then this guy divided by 3 is 140 divided by 9. And then you can also find out each charge distribution here. So what I would recommend is just take this question and then like try to solve by yourself. Okay. All right, so I'm going to move on to my next 2 questions. Anlaşılmayan bir yer var mı arkadaşlar? Nasıl gidiyor? Evet. Ses çok gelmedi ama ben devam ediyorum o zaman. Evet. Bu da arkadaşlar benim kendi kitabımızdan. That's from our book. That's 24th chapter, and the question is 27th question. So a parallel plate with area A, separation X, has plus Q and minus Q charges on it, and the capacitor is disconnected from the battery and charges are fixed. What is the total energy stored in the capacitor? Okay, so we know what is the energy. So first of all, we know what the capacity is. So capacity of a parallel plate is epsilon 0 times the area of the parallel plate divided by the distance, the distance D. And since it has like separation X, that means, divided by X. And potential, the potential energy is, you can write it in 3 different formulas, which is Q squared divided by 2C, or QV over by 2, or CV squared divided by 2. Okay, so in here, what you can write then, the energy would be Q squared divided by C, which is, so this 2 comes from this formula, and C epsilon 0A divided by X, and you can put X in the numerator here. So that's our answer. Okay, so next the question is, what if the plates are pulled apart and additional force and with additional displacement, let's say additional displacement dx. So we are making this separation a little bit higher. Okay, so what is the change in the stored energy? What is delta U? All right, so the question is this. So initially it was here, it was x distance away, and then you just like pulled apart another dx distance. So initially it was here, so this is the initial picture, and that is the final picture, right? So U initial goes from U final, and what is the difference between these two is just the separation between the plates, and one of them is x and the other is x plus dx. So that delta U would be final minus initial, and that would be like you're going to subtract this guy from this guy. So this is our change in the energy if we increase the separation by dx. Okay, so next question. The plates are attracting each other with force F. So what is the magnitude of that force F? So we know that, you know, these are plus and that is minus, right? So the parallel plates always, you know, pulls each other, right? The plus attracts the negative part, right? So positive attracts the negative. So there will always be a force between the plates. And what is that force? And so we're going to see that, and so these are the forces. So remember, this was the work done by the force and by a distance dx. Okay, so so that force, and then even if you have that force, but you are moving like at the x distance like this. So the amount of work for F to move dx is given in this formula. So work done is change in the potential energy, so you can say. And here you can write that, you know, those are the magnitudes that are being equal to each other. So that the force is then, and the next is the work is related to du. You know, remember, so this force, so remember the work is force dot dx. So so force is in this direction and dx is in that direction. Basically, this has a negative value, right? So cosine 180. And we know this work is equal to minus delta U. So this is a fixed problem, like, I mean, definition. So from physics 1, we have seen this thing. So this work is done minus delta U. So that means, you know, if this is negative part of it, so this is equal to minus f dx, and that is equal to minus du, let's say. So minus minus cancels out. So what you have is this thing, okay? And F is basically the change in the potential energy divided by dx. So we know from the previous part what du, change in the potential, is. So if we divide by dx, that's what we find. So the dx cancels out. So du is this guy divided by dx, and dx cancels out. And the force is q squared divided by 2 epsilon 0 a. Okay, the force between capacitor of the plate, between the capacitor plates. So remember, so let's think on it a little bit further. So remember, electric field of a metal surface, we take that to be like sigma over epsilon zero. Okay, so what was sigma? Sigma is the charge density of the surface, that is charge divided by area and divided by epsilon zero, and that is the electric field. And then we know, for example, if you know, if a general, so the definition is F is equal to Q times E. So if you just like follow this thing, that would be like Q times E, which is another, I'm going to make it Q, and then divided by epsilon 0A, for example. Okay, Q squared over 2A, Q squared divided by epsilon 0A. And so that's, I have written it already. But our answer is basically, so this is our answer, is half of it. Okay, so there's an extra 2 here. Okay, so it's not really equal to this force between the capacitor plates is not just equal to the charge times electric field. It is just half of it. I mean, the reason for that would be also related to, you have like positive, negative here. We always deal with the surface of the plates like this. But there is also, and then we say, whenever we look into a Gaussian surface here, this electric field, or you look into Gaussian surface like that, electric field, we only deal with the charges on the surface, but here we take that E to be 0, okay? But in reality, so if you want to take, for example, a charge plate like this, so you would see that there's an electric field here, and then there's also an electric field here. So it's like the insulator. So it's basically, since we are ignoring the part that whatever inside is, we should just like take into account of the other side of the metal part, so that then it can be just these two things will be equal to each other. But again, this is the correct version or correct value. So the force between the charges, the parallel plates, would be Q squared divided by 2 epsilon 0A. Okay. So our next question. All right. Two parallel plates have equal opposite charges. In vacuum, so they are in vacuum, basically. So the electric field of the capacity of the capacitor between the capacitor plates is this much. So in vacuum, the electric field is 3.2 times 10 to the 5 volts per meter. And when the space between the plates is filled with dielectric kappa, electric field, the new electric field, E prime, is decreased. So it's 2.5 times 10 to the 5 volts per meter. Okay, so that's with the dielectric filling. So what is the induced charge density on the dielectric surface? So that's one of the questions. And the next question, what is kappa, the value of kappa? All right, so we know, what we know is this thing. So initially it's this guy, and then finally it was filled with so let me just filled with a dielectric with a kappa. So this E prime is lower than this in vacuum. So this E prime, we know that is equal to the initial electric field value divided by kappa. So we can figure out by just taking the ratio of the electric fields and kappa to be 1.28 value. And we can also figure out, so we found out what kappa is. And we can also figure out what sigma induced is. So sigma induced is basically the charge on the dielectric surface, okay? And that's due to the electric field of the parallel plates. So next, what we can say, remember from our formula, sigma induced is sigma times 1 minus 1 over kappa. So we can find out, well, basically, where's that formula coming from? So it's coming from, so electric field is sigma divided by epsilon 0. Okay. So new electric field is sigma prime divided by epsilon 0. Okay. And so this sigma prime is the original charges minus the induced charge. Okay. Remember, when we have this formula, so how we come to think about this is this thing. Okay, so remember, if we have a dielectric surface here, so initially you have plus charges here, which is sigma, and then we will have sigma induced here. Okay, so these are like, one of them is positive and the other is negative. Okay, so this total charge is sigma prime is equal to sigma minus sigma induced. Okay, and so our E is initially, let's say, without the dielectric, is this much. Our new electric field is sigma prime divided by epsilon 0. So this sigma prime has something to do with this kappa, okay? And this sigma prime is equal to sigma divided by sigma induced over epsilon 0. So I know the value here. So I know this thing to be, what is it? 3.2. So 3.2 times 10 to the minus 5. I know this epsilon 0 value, okay? So that is 8.85 times 10 to the minus 12. So if you multiply these two guys, then you're going to get what sigma value is, okay? So this plus, all right? So you can find that out. So you can also find out from here, this E prime is equal to, sigma minus sigma induced epsilon 0. Here, sigma induced is equal to E prime times epsilon 0. So that is 2.5, right? 2.5. 2.5 times 10 to the 5 times 885 times 10 to the minus 12. Okay, that's epsilon 0. So since I know sigma from here, I can find out what sigma induced is. So, just like relating these two things. So that's the maybe just review of the last lecture. So this is the important part here. So what we say is that, since, so E, and let's say just like E prime, so what's going to happen when kappa is, let's say 1, which means in vacuum, and then when kappa is greater than 1, okay, so E prime would be E divided by kappa, okay, and then we know, for example, if this has potential V, and this will have V prime to be V divided by kappa, okay. So here we also say that if this has sigma value, this sigma prime would be sigma divided by kappa. Okay, so this kappa, and that is equal to sigma prime is equal to sigma minus sigma induced, okay, divided by, or not divided by, it's just this guy. Okay, so this this is equal to sigma prime, these two. So if you just equate these two things, right? So what we're going to have is, take this guy to the left, sigma induced is equal to sigma minus sigma divided by kappa. All right. So here you can find out that sigma 1 minus 1 divided by kappa. And that is sigma times kappa minus 1 divided by kappa. And that is our induced value. You know, remember, we have different kappa values for different materials, right? So, for example, a kappa value to be 2. So what does it mean? So kappa value is something that, you know, when you put value 2 here, sigma 2 minus 1 divided by 2, that is sigma induced, and that is sigma divided by 2. What it means is, you know, half of the initial charge is induced on the plates, on the dielectric material. So, you know, every material has different kappa, and it shows the capacity to be able to, let's say, charge on its surface. Okay. You know, that's the you know, thing about kappa. You know, remember, for example, if you put, you know, what is, for example, so you have this like metal plates, all right, like, so these are kappa plus and negative, that's parallel plates. So imagine I put a metal here. Imagine I put a metal slab here, okay? So the amount of, you know, whatever you have here, you would have the exact opposite here, okay? So this will have, if you have, you know, sigma charge here, this sigma induced in metal case will be sigma, but just negative. Well, I don't really, let me not just sigma it. Okay, so if you have like 100 positive charges here, you will have 100 negative charges. But a dielectric cannot do that. Okay, so if you put a dielectric material with a kappa, the amount of induced charges here, the sigma induced, will be less than sigma always. Okay, so that shows, and then that means, you know, this kappa is greater than 1. So in a metal case, you know, if you look at here, since sigma induced is same as sigma, and kappa value should be like very, very, let's say, I mean, it's just like greater than. So this kappa would be much, much larger, I think. So, yeah. Anyway, so that's the thing about kappa. All right, let's go back to our question. So, so you can use any of the formula that I shown you. So just like plug in the values, you can find that sigma to be 2830 nanocoulomb per meter. Okay, and sigma induced will be this guy divided by kappa, 2213 nanocoulomb per meter square. So so that's the all right, so that is the value of it. I'm trying to, okay, so that's sigma prime. So the difference between these two is gonna give us, so if you take this guy and subtract this guy, so 620 roughly, 620 now will be the induced. Okay, some rounding error that are in between. So you can use any formula that you want. Evet. Şimdi arkadaşlar benim elimdeki sorular bunlardı. Şimdi benim şey olarak nasıl diyelim? Sizin başka böyle aklınıza gelen bir soru var mı?